Okay, so let us begin with the let's find the optimal weights for this minimum variance portfolio, but we are looking for a target rate of return of 7.11%. So let us begin with A, this central piece over here, and that we essentially get it as M inverse. Okay, keep in mind that A, this expression here, it's the inverse of whatever we get from this multiplication of these three matrices. Okay, so we have M inverse, and then inside we have a multiplication of three matrices, so we will do M multi. Okay, and the first matrix is the transpose of mu1. And there we go. Now, when we get to this point, let's recall that with M multi, we can only multiply two matrices at a time. So I have three items here, three matrices. So I will need a second M multi. I can add it here. So comma M multi. So what I will be doing, contrary to what we have done in other cases, we're going to multiply the second and the third, whatever output we get from the second and the third, which is omega inverse and then mu1. That output we are going to multiply by the transpose of mu1. Okay, so in the inner M multi, the second M multi, I'm multiplying omega inverse and mu1. Let's do it. Omega inverse, M inverse of omega covariance matrix, comma mu1. Okay, so I'm multiplying here. Let me see if I'm able to highlight this. This is that M multi. So what I'm doing is simply omega inverse and mu1. I'm multiplying them. And then the output of that, then I'm multiplying with the transpose of mu1. And so now, because of those two M multis, I'm multiplying the transpose of mu1, M inverse of covariance matrix, and mu1. Three things. So now at this point, I close, right, the outer M multi, and then I close the inverse, and I'm getting this. Now, that is like an intermediate step. We don't need these values showing up here. But okay, this is we can just keep that there. But most importantly, let's keep this formula that we are going to then type in the overall formula. Let's go here. Let's delete these weights. Don't worry, this is going to go away, but we're going to get it back as soon as we plug the weights again. Now let's type the entire formula. And luckily we have this part of a formula, which is a little bit, it could be a little bit, it could get a little bit messy. We already have that done. So what we're going to do is we're going to do M multi, right? And now, once again, we have we need a lot of M multis in this case because we will have to multiply omega inverse. We have M1, we have A, this thing that we just solved, and we have B. So actually, we will need M multi, M multi, M multi, three M multis, only in this specific case. I'm gonna copy this formula later, the moment we get it. I copy it somewhere up here so you can sort of reference it and type it and more carefully. But we have bottom line 3 M multis in this case. And then the first item we are multiplying is M inverse of covariance. So it is omega inverse here. And there we go. That is the first item we are including in our innermost, in the innermost mode. That's what we're multiplying that with mu1. Okay. Now that is the first mult, these two. The output of these two, we're going to multiply with this. Okay, this lengthy formula that we already typed. Now you can do this. What we were going to do is now we have the innermost mode and it's closed. So now we multiply this output, comma, with another value, which now we're using this second outer M mode, but not the outermost, the last one. We're not there yet, but this is the second one, the second outer M mode. And what we have to plug here is this formula. So we can do something. If I try to click here, it's not going to take the formula. It's going to reference the cell. So let's go here before the equal sign. Let's add a space. And then I'm keeping this as text. Let's go here and then let's copy all this. Okay. So keep in mind, we're sort of working in little pieces. This is just this middle component here. Okay. So now we go back to our formula. Let's delete that space. So Excel, the whole point was in this, now Excel was not reading this as a formula, so we were able to go here and copy this. Okay, now we go back here, we get rid of this space, and now this is a formula again. Okay, now we have multiplied covariance of the inverse of covariance with mu1 here. And now we need to multiply the output of that with A. A is the inverse of the multiplication of mu1 transpose omega inverse mu1. So since we have it here, we just put it here like this. Okay, that was helpful. And once we get to the end, now we're multiplying the output from omega inverse mu1. We are multiplying that with A. Okay, and we can close parenthesis of the second outer M mod. Now all of this is done, but we still have one more M mod. Okay, and then what we do is one more comma. Now we're adding the last element, which is B, which is goal. Okay, so we just do B. Okay, and then B is this matrix, which is always, all of the other matrices are going to change. The higher is N, the higher the number of assets. Matrices will have different sizes, dimensions, but the B will always be a 2 by 1. First cell is going to be the return goal. The second cell is going to be just a number 1. And then I close this, right? And then by closing this, now I'm multiplying by B. Okay, and now this is it. So once I have that, then I can just type enter and we got the same values that we had gotten. This was using solver solution. And now this is the matrix solution. Isn't that cool? So now this looks like more complicated than solver. I completely understand. Uh, how or and we can get rid of this. This was like an intermediate calculation. So to avoid getting confused with so many parentheses and commas, I just solved here for A. But okay, this is an intermediate step getting A. Okay, and now we can do formula text here. And there we go. We can see that formula and we can reference it. If it helps, we can write. Okay, let me move this a little to the right. Now you have that entire formula showing up here. Moreover, let me write the entire, okay, the final formula, entire complete is, and then formula text. It's much longer. It's the one we use here. And okay. And I'm just doing that. If you can take a screenshot, you can go back to it. That's the formula that we are using, and we are using the matrix names that we gave to each one of these. This is B. Okay, this is mu1. This is W, and then this is covariance matrix. Okay, now when or how is this useful? Okay, so let's look at this quick example. Let's assume we want to explore not only a single goal, but we want to explore the minimum variance allocation for an array of goals, of return goals, right? And before we do that, now a big question here, and let me get rid of this formula here is, okay, what is the variance of this portfolio? Well, the variance of this portfolio, it's simple. We can use this formula here. Now, let me give you another, an interesting piece of information, an interesting tool. Even before we get the weights, okay, we can get the variance of the portfolio that has the lowest risk and gives you return goal in matrix B. Okay, and how can we do that? Well, we can use this formula, which is that the variance of the variance of the portfolio with the minimum risk that reaches goal listed here in B is B transpose AB. And the amazing thing is that we have A nicely separated from everything listed here. So it would look like this, equals M multi. We have three terms. So once again, we cannot use a single M multi because single M multi can only multiply two things at a time. So we need another M multi. And then the first of the three terms is transpose of B. The second of the terms is A. So we can do the same. I can just place the cursor here. I'm going to add a space. By doing that now, Excel is no longer reading this as a formula, but it is reading it as text. And now I can pause my formula there and I can go here and I can copy this formula, this amazing formula, which is A. And I need to multiply A and then B again. Then I can go back here and then I can simply paste this A here. And now I am multiplying transpose of B with A, and I can close this inner M multi. And now I closed it. So whatever the output here is, I'm going to do comma, and I'm going to follow this formula. I'm going to do B again. So it's B transpose times A, this expression here, this intermediate step, and then times B. And I close the outer multi, and then there we go. So the variance is now listed here. So the interesting thing is I don't need the weights to calculate the variance. The variance is still showing up here. And even if I don't have the weights. Okay, so let's evaluate something interesting. Let's say I would like to evaluate an array of goals. So I can get a 34.5%, a 30%, a 22%, and I would like to evaluate all of these portfolios, okay, that a 13%, a 10%, a 7%. So I can meet with somebody or I can evaluate not only a portfolio that gives me this goal alongside with the level of risk I would be taking if I were to take this portfolio. Okay, so what I can do in this case is I can use matrix operations. Okay, now if these are my goals, of course a negative 10% doesn't make too much sense as a goal, but I'm having this negative number here just for completeness. Okay, so let's rely on this interesting formula that we just got here. Okay, and then I believe it would be straightforward if we do this. I just copy this formula that we just wrote here, and let me now paste it here. Okay, if I just press enter, of course, that is giving me the variance, and then the standard deviation is the variance of this. But it's giving me the standard deviation and the variance, and the variance should not be in, it should simply be in, right, in decimal form. So the same number we already got here, because this is referencing this goal. Okay, so now what I can do is I can utilize this formula. This matrix form is giving me the variance of the portfolio with the lowest risk that reaches this goal, whatever it is. And I'm starting in minus 10% for completeness, so we will do something with that. But I'm then going all the way up to 34.5% for each one of these return goals, and I'm going to evaluate the risk, the lowest risk at which I can get those returns. And then I decide from a whole array of possible allocations that all of them have the lowest possible risk, but they're reaching these particular goals. Now, the only adjustment I need to do to make this little bit more complex problem for an array of goals instead of a single goal is I can scroll down. Okay, but if I scroll down, then what I'm going to do is I am going to change two things. Okay, here in this formula, I needed the transpose of B. And the transpose of B looks like this. Let's do it. Let's put it here. Transpose of B. It looks like this. Okay, it looks like what the transpose B looks like this. Goal 1. So if I already have the goal and a 1 in this shape, I don't need to transpose. Okay. So then what I will do is I will change here transpose B and I will directly choose this. And now this is like a B transpose, but now the goal is 10% negative and the 1 is here. Okay. Now on the same ground, here I was finally multiplying by B. Okay, but if I just select this, there will be a problem because B is a column 2 by 1, and this is now a 1 by 2. This is a row. So then I no longer need to transpose here because this is already a row. But then I do need to transpose here because now this is a row and it's supposed to be a column. Okay, so then I would do transpose of this. Okay, and there we go. So now this is giving me, everything else stays the same because mu1 is coming from up here. These are the expected returns and a bunch of ones. Covariance is coming from here. So everything is the same except that goal. We have it like here. And now we have it in a different shape. It's a row instead of a column. So I don't need to transpose here, but I do need to transpose here because now we're using a goal matrix, a B matrix that is a row instead of a column. So that's why we are changing here and here to accommodate this table and array that we will complete. Once we have done that, we can keep everything has a name, mu1 covariance. So these references are not going to change if I scroll down. But I'm sorry, here. But this goal, which is now a row, that is going to change when I scroll down. So what I'm going to do is I will take these two values and I'm simply double click. I place the cursor here. It's a smaller cross. And then I double click. And then it's filling all of the values for all of the goals. So what am I getting here? This is the standard deviation that corresponds to a portfolio that holds the portfolio that you can form where you can reach the lowest possible risk that gives you a 15%. So now you know if I'm interested in a 20%, you would need to tolerate a 51% standard deviation. So once you have an array like this, decision making becomes a little bit more um, convenient because now you're choosing from an array of possible combinations And then, of course, we have portfolio theory, and but all of these portfolios, at least, they are they're not dominated by another portfolio because for these levels of goals, then this is the lowest cost you can at which you can get it. If we think about standard deviation as the cost that you accept to get returns with you from a return shop, right? Now, if we just select all of these standard deviation and all of these goals, we could do something quite interesting. We could insert here some scatter, right? And then that would look amazing. So this would be minimum variance frontier. Uh, and what this is essentially capturing is the same you have in that array, but in a visual way. And then for each, the y-axis is essentially the different return goals or the return that each one of these portfolios is giving you. And then the x-axis is essentially it's measuring the level of risk you're accepting. Okay, so yes, of course, when we have the efficient frontier, then if we look at some portfolios, right, we would look at you can get the same level of for the same level of risk, you can get essentially a negative return or you can get a positive return. So this part of the frontier is we often call it a inefficient portion of the frontier, or the upper part of it, we call it the efficient frontier. Um, um, if we're only considering a universe of risky assets here, we're not considering the risk-free rate yet. Okay, because this is the efficient frontier, because then these uh, for every possible allocation that you have for the same level of risk, this is the portfolio that is giving you the highest possible level of return. I mean, it's easier to understand that this is the inefficient portion of the frontier, this one is below, because it's all of these points you for if you're taking 20% risk, then why would I get this negative return if I could get a portfolio with a 20% of standard deviation, but giving me close to 10% positive expected return, or 20% in 19%, and so on. We would need to zoom it a little to be able to look at that chart in a better way. But long story short, going back to the case of solver, if we try to do something like this with solver, we would need to solve each one of these rows one by one, one by one, one by one. But by using some matrix operations, we can quickly type one formula, scroll it down, and then we can get a multitude of combinations and portfolios that we can graph, we can evaluate, we can study and analyze in a snap. So a problem like this would not be possible, or at least it would be incredibly challenging, especially if you have a large number of assets. And that is why, okay, this looks a little complicated, but in some complex problems, it handling or knowing our way in terms of matrix operations, it pays off. Okay, so thanks for your attention, and let's keep in touch.